Let's solve this physics problem involving the motion of an electron between two-point charges. We have two-point charges, a positive charge of 20 nanocoulombs and a negative charge of 12 nanocoulombs, separated by 50 centimeters. An electron is placed on the line between the charges at a point 10 centimeters from the negative charge. It's then released. What is its velocity when it is 10 centimeters from the positive charge? Let's first sketch this scenario to visualize what's happening. We'll represent our charges as points on a line. Here on the left, we have our positive charge Q1, which is 20 nanocoulombs. And here on the right, we have our negative charge Q2, which is negative 12 nanocoulombs. The distance between them is 50 centimeters. Initially, the electron is placed 10 centimeters from the negative charge, which means it's 40 centimeters from the positive charge. We want to find its velocity when it reaches a point that's 10 centimeters from the positive charge, which would be 40 centimeters from the negative charge. Because the electron has a negative charge, it will be repelled by the negative charge and attracted to the positive charge. So both forces will push and pull the electron toward the left, accelerating it in that direction. To solve this problem, we'll use the principle of conservation of energy. Since the only forces acting on the electron are the electric forces, which are conservative, the total mechanical energy of the electron is conserved. This means that the change in the electron's kinetic energy equals the negative of the change in its potential energy. Delta K equals negative delta U. Initially, the electron is at rest, so its kinetic energy is 0. At the final position, the kinetic energy will be 1/2 mv squared, where m is the mass of the electron and v is the velocity we're trying to find. The potential energy of the electron is related to the electric potential V by U equals Q times V, where Q is the charge of the electron, which is negative E. Let's expand our energy equation. The change in kinetic energy equals the final kinetic energy minus the initial kinetic energy, which is just the final kinetic energy, since the initial kinetic energy is 0. This equals the negative of the change in potential energy. The change in potential energy equals the electron's charge times the change in electric potential, negative E times V, final minus V initial. Rearranging, we get 1/2 mv squared equals E times V initial minus V final. Solving for V, V equals the square root of 2E times V initial minus V final divided by M. Now, we need to calculate the electric potentials at the initial and final positions of the electron. The electric potential due to a point charge Q at a distance are as given by V equals K times Q divided by R, where K is Coulomb's constant. Since we have two charges, the total potential at any point is the sum of the potentials due to each charge. V equals K times Q1 divided by R1 plus K times Q2 divided by R2. At the initial position, the electron is 10 centimeters from the negative charge, so R2 equals 0.10 meters. And it's 40 centimeters from the positive charge, so R1 equals 0.40 meters. At the final position, the electron is 10 centimeters from the positive charge, so R1 equals 0.10 meters. And it's 40 centimeters from the negative charge, so R2 equals 0.40 meters. Let's calculate the potentials numerically. First, we need Coulomb's constant. K equals 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And we need to convert our charges to coulombs. Q1 equals 20 nanocoulombs equals 20 times 10 to the minus 9 coulombs. Q2 equals negative 12 nanocoulombs equals negative 12 times 10 to the minus 9 coulombs. For the initial position, the potential is V initial equals K times Q1 divided by R1 plus K times Q2 divided by R2 equals K times the quantity Q1 divided by 0.40 plus Q2 divided by 0.10. Plugging in our values, V initial equals 8.99 times 10 to the 9th times the quantity 20 times 10 to the minus 9 divided by 0.40 plus negative 12 times 10 to the minus 9 divided by 0.10 equals 8.99 times 10 to the 9th times the quantity 50 times 10 to the minus 9 minus 120 times 10 to the minus 9 equals 8.99 times 10 to the 9th times negative 70 times 10 to the minus 9 equals negative 629.3 volts. Now, let's calculate the potential at the final position. V final equals K times Q1 divided by R1 plus K times Q2 divided by R2 equals K times the quantity Q1 divided by 0.10 plus Q2 divided by 0.40. Plugging in our values. V final equals 8.99 times 10 to the ninth times the quantity 20 times 10 to the minus 9 divided by 0.10 plus negative 12 times 10 to the minus 9 divided by 0.40 equals 8.99 times 10 to the ninth times the quantity 200 times 10 to the minus 9 minus 30 times 10 to the minus 9 equals 8.99 times 10 to the ninth times 170 times 10 to the minus 9 equals 1,528.3 volts. Now we can calculate the velocity using our formula. V equals the square root of 2e times v initial minus v final divided by m. First, let's calculate the potential difference. V initial minus V final equals negative 629.3 volts minus 1,528.3 volts equals negative 2,157.6 volts. We need the charge of an electron. E equals 1.602 times 10 to the minus 19 coulombs. And the mass of an electron, m, equals 9.11 times 10 to the minus 31 kilograms. Now we can calculate the velocity. V equals the square root of 2 times 1.602 times 10 to the minus 19 times negative 2,157.6 divided by 9.11 times 10 to the minus 31. Wait, there's an issue here. The potential difference is negative, which would give us an imaginary velocity. This doesn't make physical sense. Let's review our approach. Let's correct our approach. The key insight is that the electron will spontaneously move from a position of higher potential energy to lower potential energy. Since the electron has a negative charge, it will move from regions of lower electric potential to regions of higher electric potential. So our formula should actually be V equals the square root of 2e times V final minus V initial divided by m. Now the potential difference is V final minus V initial equals 1,528.3 volts minus negative 629.3 volts equals 2,157.6 volts. As the electron moves from its initial position to its final position, it is accelerated by the electric field. It gains kinetic energy equal to the negative of the change in its potential energy. Now, let's calculate the electron's velocity correctly. V equals the square root of 2e times V final minus V initial divided by m equals the square root of 2 times 1.602 times 10 to the minus 19 times 2,157.6 divided by 9.11 times 10 to the minus 31. Calculating this, V equals the square root of 2 times 1.602 times 10 to the minus 19 times 2,157.6 divided by 9.11 times 10 to the minus 31. V equals the square root of 7.59 times 10 to the 14. V equals 2.75 times 10 to the 7 meters per second. This is a very high speed, about 9% of the speed of light. At this speed, relativistic effects would start to become noticeable in a more precise calculation. However, for this problem, we're using classical physics, which gives us a velocity of 2.75 times 10 to the 7 meters per second. To summarize what we've learned, we solved this problem using the principle of conservation of energy. We calculated the electric potential at the initial and final positions of the electron, then found the resulting velocity. The velocity of the electron, when it is 10 centimeters from the positive charge, is 2.75 times 10 to the 7 meters per second. A key insight was recognizing that the electron, having a negative charge, moves from regions of lower electric potential to regions of higher electric potential, which corresponds to moving from higher potential energy to lower potential energy.